thrilled. So my name is Jess. I go by with she, her pronouns. I'm a PhD student at the University of Victoria. I started my PhD in 2020, and I hope at the end of tonight to leave you with just an impression of how incredible the line of pursuits of planet formation really is. This is what I've been working on for the last 4 years. I feel very privileged to be able to work with real astronomical data, collaborate with astronomers around the world, travel to different research conferences, travel to telescopes, and try to distill all of that into a little bit of a presentation for you to give you a taste of what it's all about. So I'm expecting this to be about half an hour, and then I hope we'll have lots of time for questions. So please, if you have questions, save them for the end. So I'd like to start our story here at home. So this is our solar system, just the 4 innermost terrestrial planets. Each pale blue dot here is one of the terrestrial planets in our solar system, and the dashed circles represent their orbits, right? So we all kind of live on the same orbital plane. The innermost pale blue dot is Mercury, then to its upper left is Venus, that's us, right there at 12 o'clock, and down below that represents Mars. Our sun is relatively old, about 4.5 billion years old, and our solar system is relatively quiescent. And of course, I haven't mentioned the gas giants in the outer solar system, Jupiter, Saturn, Uranus, and Neptune. But I'm starting here with our solar system to scale, because I want to tell you about other planets around other stars that are not the sun. So this graphic right here represents some of the other solar systems that we know about, planets going around stars that are not the sun. So every single dot here represents a planet, and the circles again are their orbits. So what we can instantly recognize is how diverse all the different solar systems out there really are. The color of the points corresponds to their temperature. So if they're blue, they're relatively cool, like our terrestrial planets. But you can see that some go as high as thousands of degrees, making them basically lava worlds. The other thing that you can notice is that this giant dashed circle here, that's the orbit of Jupiter. So many of the exosolar systems that we know of, the orbits are very, very small. They go around their stars in hours or days, which really lends to their detectability, but also gives you a sense of how different things can really be out there. So this was a compilation made in, if you look up there, 2010, back when we knew of just a few hundred exoplanets. But since then, we've discovered many more. So I want to take us back in time to look at how many exoplanets we discovered over the years. So going back to early 1990s. So this is a picture of the full sky. Thank you. So right here we can see the galactic plane. The dark clouds that you see are clouds of dust where starlight is absorbed, which makes it appear dark. And down here in the south we have the small and large Magellanic clouds. Okay, so in 1991 we knew of 0 exoplanets. We just knew of the planets in our solar system. In the top left and top right corners you'll see counts of the different types of exoplanets discovered by different methods. So we have the radial velocity method, transit, imaging. Let's hope that quiets down. And as I play the movie, we'll see the count start to increase. There we go. 1995, the first planet around a sun-like star. So can everyone see these dots starting to appear all around the sky? Here we go. 2K, year 2000. Most of the planets at this point discovered by the radial velocity method. They're just popping up. Now we're going transit method, direct imaging, microlensing, and soon the advent of Kepler. We'll start to see many planets appearing in this region of the sky here, colored purple for the transit method. Here they come. All right. closing in on, okay, more than 1,000. Kepler discovered thousands. All of a sudden, we're adding 2,000, 3,000, coming up to 2020 now, closing in on 4,000. Different, more obscure methods are being used to increase the number further, and here we are, 2022 at 5,000. And actually, if you go on the exoplanet catalog today, we've closed in on 5,700, with 7,000 more candidates waiting to be confirmed. So the sky is full of planets. And you'll see that not every single star here has a circle around it. Not every single exosolar system is in the right geometry for us to be able to observe the planets around those stars with our methods. But using statistical arguments, based on the number of planets we've observed and the number of stars we've observed them around, we think that every star has at least one planet around it. So the question is, where do they come from? How are these formed? How does every single star have a planet around it? So I want to tell you about the wombs of pregnant stars, right? How do stars give birth to planets? How does every star host a planetary system? So with this schematic here, I'd like to introduce the planet formation environment. So in this artist rendition, what we see is a disk, edge on, so it appears along this dark band here. And this is what we call a circumstellar disk, or a protoplanetary disk. It's a disk of gas and dust that swirls around the star. It's held together by the star's gravity. It's very similar to our own solar system. I mentioned that all the planets orbit in the same orbital plane. This is the same plane as the disk that originally formed our solar system would have had. So in the center is a young star. Stars give birth to planets when they're young. We all wait until we're 20 or 30 years old, but stars form planets almost immediately after they're born themselves. So to really understand how a young star gets a disk, we need to zoom out. We need to understand how stars form. Planet formation is really a byproduct of star formation. So where do stars live? How do stars form? So now I'd like to introduce you to the star formation environment. It's a giant molecular cloud that exists in interstellar space. So what happens to a giant molecular cloud? A cloud of gas and dust, very diffuse, but denser in some regions than others. So this is a numerical simulation now, not an artist rendition anymore. This is a giant sphere of gas. And these numerical simulations were performed by Matthew Bates in the UK. And basically, we have a giant cloud of gas. We initialize it with some turbulent velocities, and we just watch what happens. Let the thing collapse under its own gravity. So immediately, we start to see filaments forming. Regions where the gas is condensing. The higher gravity you have, the more material you pull towards yourself, the more gravity you have. It's a bit of a runaway process. Eventually, when the gas gets dense enough to form cores, and those cores collapse, we get stars. So each one of these white points here is a star. You can see many, many stars being made, all from the same stellar nursery. These giant molecular clouds are stellar nurseries. All of these stars are very young. They all inherit the sort of same gas from their natal cloud. We can also see it's a very chaotic environment, right? Stars flying all over the place. Let's zoom out and take a bit of a three-dimensional view to see really what is the structure of this thing. So these exist out there in space. If you've seen, for example, the constellation Orion, the Orion Nebula looks something like this. It's a region of space where a cloud has collapsed and is forming stars right now, today. Okay, so more on that same movie. Now I'm showing you a movie where we are looking at the stars that formed in the previous movie. Right now we just have one star that's formed, but soon this whole screen is going to be filled. So each panel tracks the life, the beginning of each star as it collapses from a core and goes on in this chaotic way to interact with the stars around it and the gas around it. There's a period of a few million years where the material that went into forming the star has not yet gone away. It's left over. It surrounds the star. And we get this interaction, gravitational interaction, with other sort of cloudlets in the cloud, as well as other stars. So what do we take away from this kind of simulational work? We see that every star has a disk for some amount of time. We're talking a few million years. And somehow, out of this disk, planets form. Okay, I want to transition now to some actual data. Let's look at the data. What do our observations show? So the telescope that I worked the most with is called ALMA, the Atacama Large Millimeter or Submillimeter Array. Here are the antennas of ALMA, located in Chile, northern Chile, on the in the Atacama Desert, which is how it gets its name. And fun fact, the acronym ALMA means soul in Spanish, so it's really aptly named. The millimeter in its name comes from the fact that it's a radio telescope. It looks at wavelengths of light of order 1 millimeter in wavelength, which puts that light in the radio region of the electromagnetic spectrum. But this telescope is not just a Chilean telescope, it's an international collaboration. It's a partnership by many countries around the world. The National Radio Astronomy Observatory in the States, ALMA is of course located physically in Chile, ESO, the European Southern Observatory in Europe, the NAOJ, National Astronomy Observatory of Japan. But ALMA also has regional centers around the world, and actually you pass one of them tonight on your way up here to this building. NRC Herzberg is one of the ALMA regional centers, and in fact contributed instrumentation to each one of these antennas. There's about 50 in total. Each one needs receivers, and NRC built the band 3 receivers, so one for every single of the antennas. Here's what it looks like on the ground. So each of these antennas work together as one single telescope. They all point in the same direction on the sky. By doing this, we have more collecting area, and we can have higher sensitivity. From personal experience, I can tell you this is a really incredible place on Earth. It's 5,000 meters in elevation. So you see how dark the sky is? It looks almost like you're in space. It's because you almost are. 5,000 meters of elevation is very little atmosphere above you, which is perfect for observing conditions. It's also very, very dry and very low oxygen as well. But what's so special about ALMA is how many antennas it has and how the antennas are distributed. The farther away they are, the better the resolution on the sky we can get. So that's the reason for having so many antennas and for spreading them out, sometimes to 16 kilometers in a largest baseline between two antennas. That really makes ALMA a high angular resolution machine. It's like a camera that takes really high resolution pictures. That's what ALMA does. That is how it helps us understand the planet formation environment. So what did ALMA see when we first pointed it at a young star? This was the first image ever taken by the ALMA telescope of a protoplanetary disk, of the dust and gaseous disk around a young star. This is called HL Tau. It was released in 2015. And this blew the minds of astronomers around the world. Why? Because it's structured. Before ALMA, you have to understand, disks around young stars were just blobs. They're just unresolved blobs. Can't tell what's going on there. Here with ALMA, because of the high angular resolution and the high sensitivity, we can start to resolve what these disks look like, and they have substructure. And that tells us that something's going on here. What we're detecting here is emission from dust grains, tiny dust grains of roughly 1 millimeter in size. And something is organizing them. You can imagine dust in this room right now. It's just kind of all equally distributed in this fluid of gas. A protoplanetary disk is a similar situation. It's mostly gas, but also dust. And something is organizing the dust into nice, clean rings. So what could that be? What could be causing this? Of course, our first thought was planets, right? Planets are forming in these disks. They're there. We just can't see them. But they're orbiting around the star at the center. And they're carving these gaps, annular regions of darkness, as they go around the star in their orbits. They must be there, we just can't see them. So that really launched the field of planet formation. You can imagine this is very exciting. Hidden planets, evidence that they're there, forming around young stars. Let's go after more. So that's launched the D-Sharp Large program, the disk substructure at high angular resolution program. ALMA stared at 20 more young stars to see what substructures are there. So this is a gallery of all the 20 disks observed, and you can just see how diverse they are. All of them have some kind of substructure, some kind of pattern to their emission. There's a star in the center, there's dust all around, and the dust is organized into shapes. So since then, we've really started to build up a more statistical sample. So this compilation was compiled by Nika van der Merel, who worked at NRC Hertzberg for a couple years. She's now in Leiden in the Netherlands, but you might have heard of her if you've been with the FDAO for a while. So in this gallery we see that the morphology of disk substructures is also diverse, just like the exoplanet population. Each one of them is different. Each one of them is unique. Each young protoplanetary disk, something different is happening in every single one of them. But they do have one thing in common. We can start to, as astronomers like to do, put things in buckets. We can recognize common structure within the whole population and try to understand common processes that must be happening within each of them. Okay, so let me take you through some of the buckets that we like to sort all these disks into. So the first sort of category of substructure are rings with cavities. So we think that if you could deproject the disk, the orbits would be circular, but because we're seeing them edge on with some geometry on the sky, they start to look elliptical. So each one of these rings represents a collection of dust that for some reason has been trapped and has not distributed everywhere in the disk. It's just a ring of material. And specifically, when we start to look in the center where the star is, which is very dim at radio wavelengths, so we don't see the star itself, it's devoid of dust. For some reason, there's what we call a cavity. The second substructure category is rings and gaps, but no cavity. So if you look in the center of each of these images, you'll see dust emission, so brightness density there that has not been cleared. So sometimes there's stuff around the star, sometimes you have to wait a bit, and then there's stuff around the star. And some of them have very, very fine rings, and some of them have very thick rings. The third category is arcs. So these sort of arc-like features that are present some azimuthal amounts around the star, but not all the way around. So not like a perfectly symmetric ring, but for some reason, just a little bit of a ring. And finally, my favorite category, spirals. Spirals are the most interesting because they are the most non-axisymmetric. There must be something driving these arms. They would otherwise be eventually smoothed out. there must be some either gravitational perturber or some kind of dynamical, continuously driving perturber happening here. Otherwise, just purely by hydrodynamic arguments, you expect it to have been smoothed out. So these are particularly interesting. Okay, so right, I said that the disk is made of gas and dust is actually just a small component by mass, only about 1%. So ALMA has another observing mode. It can also look at the gas. So here's an animation showing you both the dust and the gas at the same time. So in blue is an animation showing just the dust component. And in the red and yellow, we see the gas. The dust and the gas is moving, but because to see the gas, we have to look at spectral line emission, we get some information in the frequency domain. Yeah, so because the gas is rotating, and it has some redshift and blue shift relative to us as it goes around the star, we can separate what gas is moving at what velocity. And we take that information at multiple velocity bins, and we put them together, and we see a movie like this. When we collapse that velocity information into just one big picture, then we get something like this at the end. So, of course, we wanted to do this for more disks. We want to see as many as possible. So here I'm showing you another large program, something that takes hundreds of hours of time on the ALMA telescope to collect. Every row here is a different disk, and every column is a different molecule of gas. So when I play the movie, we'll see that familiar, what we call butterfly pattern, which comes from the fact that the disk is rotating. The gas is going around the star, and we only capture the line of sight velocity component. So looking at just one row, all of that is the same disk, but within that disk are different molecules, and they're distributed differently. And coming back to the diversity, the different molecules that exist and the different morphologies that they have. So when we take the same information and collapse it along the velocity component to create just a regular image, this is what we see. Again, one row, one disk. The different columns are different molecules. This is telling us something about the chemistry, the chemical diversity of the disks. Different density, different temperature, different dust grain chemistry can be happening to create different substructures and different extents of emission as well. It's really just like a zoo out there, not just from one disk to the next, but within one disk, if you look at different tracers, different molecules, you see something different. There's a lot going on here. Okay, but we want to find planets, right? Somewhere in here there's planets. So let's dive deeper. Let's look closer. Let's ask the question, if we look really, really closely with ALMA, if we stare for a long time, if we make use of its angular resolution, can we find planets? Has ALMA found baby planets? So this is a representation of what we think should be happening. Somewhere embedded in the disk, there are planets. So I'm happy to tell you, the answer is yes. This here is our very first image with ALMA of a baby planet, a planet that is not yet finished forming. Can anyone see where it is? Right there. That is Pedia 70b. It was discovered in 2021 by Marian Benesty. And again, blew our minds, right? There it is. Young star, baby planet. If we, again, make use of some artistic liberty here, we can understand that we're not just seeing the planet. We're seeing the disk around the planet. So stars have disks around them. Planets have disks around them too. So out of this disk, the planet itself is accreting, is growing, is forming. And the leftovers of planet formation will go into moon formation. So we get this recursive idea. Leftovers of star formation create planets. Leftovers of planet formation create moons. That's not the only one. So here we have another directly imaged planet, this time not with the ALMA telescope, but with the VLT. And what's special about this one, so the planet is circled there just at about roughly 10 or 11 o'clock. What's special about this one is that we've observed it over different years. So we can actually see it orbiting around its star. Here we go in 2015, 2017, 2019. So it's orbiting clockwise for us on the sky. This is what baby planets look like. Isn't it thrilling? Okay, I'm coming up to the end of the talk here, but there's one more baby planet that I'd like to introduce to you. This one's near and dear to my heart. This is the disk around the star called AB Aurigae. Again, the star is at the center, but we're looking at wavelengths where the star is not bright, so we don't see it. This disk is exquisite. Look at that structure. Again, this is not the ALMA telescope. This is VLT, different wavelength of light, different dust being traced, but exquisite substructure. Where's the planet here? Right here. So this is a composite image. I'm showing you observations of the same disk, but at different wavelengths taken from different telescopes. And in the blue colored emission here, we have a candidate protoplanet known as AB Aurigae b. It's quite famous, you might know it. But this is a very, very young planet. If it really is a protoplanet, it's the youngest one that we know. So young that it almost looks indistinguishable from the disk itself. Analyzing its spectra, it's very difficult to tell whether this is a separate gravitationally bound body or just a piece of the disk that kind of mimics what a planet looks like. So this area of research is still very active. We want to find the baby planets, but it's very difficult. So I'd like to leave you with just a couple thoughts. The first is going back to the very first slide, or one of the first slides where we looked at the number of exoplanets discovered over time, going back to the early 90s. Those are fully formed planets, right? Their stars are very old, billions of years old. What we're trying to do now is look for the youngest planets, the ones that are still forming. And so far we have, 2.5. So we're still in those very early years. It's a very exciting time to work in this line of research. And the second thought I'd like to leave you with is, it blew my mind the first time I realized that we owe everything we have on Earth to the disk that the solar system formed from. The molecules and the dust, they're all distributed differently. They have different conditions at different locations in the disk, and the planets just inherit them. So yeah, that just really blew my mind when I first had that thought. Okay, that's it for me. I'd love to take your questions. Thank you so much for listening.